Okay, so we've talked about Lewis diagrams, and now we're going to talk about the times when we need to improve on or change our... So the first circumstance that we're going to talk about, we first need to talk about what Lewis diagrams assume. So the first circumstance we're going to talk about is called resonance. So first we need to talk about the idea that in a Lewis diagram, we're assuming that the electrons are localized. That means that we are assuming that they're shared between only two atoms. But empirical data tells us that's not always the case. So we need to expand the way that we draw Lewis structures so that we can reflect reality. So the first example that we're going to work with is the nitrate ion. So that's NO3 minus 1. And we're going to follow the same rules as we've been following for writing Lewis dot structures. So we're going to say that we have 5 valence electrons in nitrogen, 3 times in oxygen, and 1 extra. So we're going to have to that the nitrate ion doesn't bond and 2 longer bonds, but instead has 3 bonds that are all the same length. So how can that be? The answer lies in the idea that the electrons are not localized, but in fact these extra 2 electrons are delocalized in what we call a molecular orbital over all 3 of these oxygen atoms. So how can we reflect that with something as simple as a Lewis structure? So we're going to reflect that by drawing it as if there's a double bond here, or drawing it as if there's a double bond here, and finally drawing it as if there's a double bond here. So we're going to draw 3 different structures. One is the one we just drew. And I'm just repeating it so we can see what this looks like when we do all of them. And then we have the brackets and the -1 charge. We're going to draw a double-headed arrow, and now we're going to repeat the drawing, but now we're going to add the double bond in a different location, one of the other 2 locations. These are called comparable structures, or potential structures. So we're also going to add the brackets here, and we have one more place that we can put that double bond, so we're going to draw 1 more arrow, and we're going to draw yet another resonance structure where we're putting the double bond this time to the oxygen down here. And yes, it is a little bit cumbersome to have to write the 3 different structures, but this represents more the reality of what's happening in this molecule, or in this case, in this polyatomic ion. And so that's how we're going to write resonance structures. In reality, the actual structure is some hybrid of these 3. Okay, let's talk about another example of resonance. So we're going to find a piece of paper that doesn't have polka dots all over it. There we go. All right, and we are going to talk about the ozone molecule. So the ozone molecule is an allotrope of oxygen. That means it's oxygen in a different form than the one we typically see. It's not O2, it's O3. Okay, so we have 3 oxygen atoms, so that's 3 times 6 for 18 valence electrons. We're going to put an oxygen in the middle and an oxygen on either side, and then we're going to put the bonds in between them. And we have, so we've used up 4, we have 14 valence electrons remaining. 2, 4, 6, 8, 10, 12, and here's 14. And we can see that both of the peripheral oxygen atoms have their valence electron octet satisfied, but this central oxygen has only 6. So one more time, we're going to take one of those lone pairs and make it a double bonding pair. But now we have the situation again where we have 2 equally valid places for this double bond. So we're going to draw the other structure, where the double bond is on the other end. And because even though these aren't ions, these are resonance structures, we're going to go ahead and put them in the brackets and draw the double-headed arrow. So that's how we write resonance structures, and they represent the reality of what's really happening. So let's talk about the next place where Lewis dot, the rules that we've learned for Lewis dot structures might let us down just a little bit. And that is when we have several different circumstances, but where the atoms involved don't necessarily obey the octet rule. So we have some exceptions to our octet rule. So we're going to talk first about probably the most unusual exception to the octet rule, and that's when you have an odd number of valence electrons in either an ion or a molecule. So the example we're going to use here is the nitrogen monoxide molecule. We very often see these with nitrogen compounds because nitrogen has 5, and yet it is relatively stable with an odd number. So nitrogen has 5 valence electrons, oxygen has 6 valence electrons, we have 11 valence electrons with which to work. So we have nitrogen, we have oxygen, we're going to draw a bond in between. I've now used up 2 of those valence electrons, and we're going to add valence electrons to this peripheral atom. I've used up 6 of my valence electrons. I have 3 remaining, so I'm going to put 2 here and 1 here. Now, we could stop at this point. Oxygen has 8, nitrogen has 5, but we do want to get nitrogen closer to having a full octet, so we're going to take this pair and we're going to make it a double bond. Now, nitrogen is still not at a full octet. Because there's an odd number, it's simply not possible, so we're going to have to leave this one as it is. Okay, so the next exception, and one that you might remember from honors chemistry, is that there are several elements that are satisfied with less than an octet. So, obviously the cleanest example and easiest example of that is hydrogen or helium. But there are also several others that can be satisfied with less than an octet, and those are beryllium, boron, and aluminum. So if we think about aluminum tribromide, and you might at first think that this aluminum tribromide is an ionic compound, because aluminum is traditionally considered a metal, although technically it can be considered a semi-metal as well, and bromine is a non-metal. But if you look at their electronegativity values, they are so close that this actually forms a polar covalent bond rather than an ionic bond. So we know that aluminum has 3 valence electrons, each bromine has 7 valence electrons, so we have a total of 24 valence electrons. We're going to put the aluminum in the center, and we're going to surround it with the bromine atoms. And we're going to draw the bonds representing the bonding pairs. We've used up 6 electrons. We have 18 remaining. We're now going to take those 18 and we're going to allocate them to the bromine atoms. We now have the octet satisfied on all 3 bromine atoms, but we do not have the octet satisfied on the aluminum atom. But aluminum is an exception to the rule. It can be satisfied with only 6. So we're going to leave this alone. At the end, we'll talk about formal charge and how we would make a decision about whether we should double bond or not. For now, you can stick with the simple rule that halogens don't double bond. Okay, one more exception, and that is those elements that can have more than an octet. Generally speaking, these are elements with at least 3 energy levels. And the reason that they have to have at least 3 energy levels is that in order to exceed the octet, the atom must have d orbitals available in order to go past electrons in just the s and the p orbitals. So let's talk about a couple examples of those elements that exceed the octet. So we'll start with phosphorus pentachloride. So if we start with phosphorus pentachloride, phosphorus has 5 valence electrons. Each chlorine has 7 valence electrons. We have a total of 40 valence electrons. So as usual, we're going to put the phosphorus in the center, and we're going to surround it with chlorines. Okay, and we're going to add the bonds. So phosphorus is now bonded to all 5 of those chlorines. And again, we'll talk about formal charge so you know why later on we'll have better justification for why we do this. We cannot attach a chlorine to a chlorine and to a phosphorus. So we can't make a chain here because chlorine only forms 1 bond. So we've used up 10 of our valence electrons. We now have 30 valence electrons remaining. So I'm going to go ahead and allocate valence electrons to chlorine. I've used 6. I've used 12, 18, 24, and finally 30. So you can see that each chlorine has its complete octet, and phosphorus actually has 10, so it's exceeding the octet. And because it's in energy level 3, it can do that. It has empty d orbitals. So remember, if it's in energy level 3 or higher, meaning that it's in period 3 or below on the periodic table, then it can form greater than 8. Okay, let's talk about how we make decisions on when we exceed the octet, when we have the best structure possible. So the way that we do that is this idea called formal charge. And formal charge is calculated by finding the number of valence electrons of the atom and subtracting the number of electrons assigned to that atom. And when we talk about the number of electrons that are assigned to that atom, we mean the number of electron pairs that you've written, that you've drawn on that, as well as electrons in pairs. Sorry, not the number of electron pairs, but the number of electrons in pairs, as well as half of the electrons in bonding pairs. So, what does that mean? Let's look at an example. And that example is going to be sulfate ion. Now, you've probably drawn the sulfate ion before, certainly in Honors Chem at some point when we drew Lewis diagrams, I had you guys draw sulfate ion. So, sulfate ion, SO4, 2 minus, and so we have 6 valence electrons in sulfur, 4 times 6 valence electrons in oxygen, and 2 extra valence electrons because it's a -2 ion. So we have a total of 32 valence electrons. We're going to put the sulfur in the middle, and we're going to add the oxygens all around the sulfur. Sorry, I forget and draw the bonds first. Okay, I've now used up 8 of those valence electrons. I have 24 remaining, so we're going to go ahead and put them on the oxygens. And this structure looks all pretty and clean and symmetrical, and you guys are generally very, very happy with this structure as it's drawn. So why complicate things? Because empirically we can see that this is not actually what the structure of this looks like. So we've got to develop some tools so that we're better at drawing structures that actually look like what they are in real life. So, formal charge. We're going to find the number of valence electrons. Well, oxygen has 6 valence electrons. All 4 of those oxygens, I'm just going to write the number 6. And sulfur also has 6 valence electrons. This oxygen is assigned 1, 2, 3, 4, 5, 6 lone pair electrons, and then half of these 2. right? So we can actually just count that bond. So we have 6 minus 7. And that gives this a formal charge of -1. All three of these other oxygens are exactly the same, so we're going to do 6 minus 7 equals -1, minus 7 equals -1, minus 7 equals -1. But the sulfur with 6 valence electrons is only assigned 1, 2, 3, 4 valence electrons. 8 electrons in its orbital, but it's sharing all of them, so it's only assigned 4. So we have 6 minus 4 equals +2. Now, the best structure, the best Lewis diagram, is the one that has the most 0 formal charges, and if getting all zeros is not possible, assigns the negative charge to the most electronegative atom. So, can we get this closer to 0? Well, if I take this pair and I put it here as a double bond, because sulfur is in energy level 3, so it can exceed the octet. That now gives this oxygen 1, 2, 3, 4, 5, 6. So instead of 6 minus 7, we have 6 minus 6, and we now have a formal charge of 0. Let's do it again. 6 minus 6 equals 0. So now I still don't have it all the way to 0, but if we look at sulfur, it now has 1, 2, 3, 4, 5, 6 electrons assigned to it, so it now has a formal charge of 0. So now I have 3 atoms at a formal charge of 0, and 2 atoms, which are the more electronegative atoms, at a formal charge of -1. So we're going to stop there. Now you might ask why we don't go one step farther. If I made this a double bond and this a double bond, it would make both of these 0, but it would make sulfur have a formal charge of -2, and that's the less electronegative atom, so it's not going to be the one that winds up with a negative formal charge. Okay, let's do one more example that is less about where to place double bonds and more about how we actually put the molecule together. Okay, so our final example is going to be this molecule, CH2O. So in this case, we're not going to be talking about where to place double bonds. We're actually going to be talking about the structure of the molecule, because there are a couple of different ways to write this molecule. So we have 4 valence electrons in hydrogen and 6 valence electrons in oxygen for a total of 12 valence electrons. So we can start out by putting carbon in the middle and putting oxygen and hydrogen around it. So if I put these bonds in, I've now used up 6 of my valence electrons. I'm going to use 7, 8, 9, 10. Now, I could put these 2 here, but I recognize that this carbon only has 6, so I'm going to go ahead and make that a double bond. This is a valid structure for this molecule, CH2O. But you guys always like to ask, how do I know that it doesn't look like this? C-O-H. Let's see, let's put the other H over here. So I've used up 6. We could even go one step farther. We can write O, H, 2, 4, 6, 8, 10, 12. So how do we decide between these three valid structures? We look at formal charge. Carbon is assigned a valence electrons of 4, and it has 1, 2, 3, 4 electrons assigned to it. Hydrogen has 1 valence electron, and it has 1 assigned to it. Again, 1 minus 1. Oxygen has 6, and it has 1, 2, 3, 4, 5, 6 assigned to it. So, in this structure, all of our formal charges are 0. Now, if we look at this structure, we have hydrogen, it has 1 minus 1, so that's a formal charge of 0. Carbon is 4 minus 1, 2, 3, 4, 5, minus 1. So that's a formal charge of minus 1. Oxygen has 6, and it's assigned 1, 2, 3, 4, 5. So that gives oxygen a formal charge of plus 1. And hydrogen again has a formal charge of 0. So, first of all, this structure gives us 4 0 formal charges, and this structure gives us a negative formal charge on the less electronegative atom. So we can rule this one out. Let's take a look at our third structure. So here we have carbon with an valence electron number of 4. And we have 1, 2, 3, 4, 5, 6. 4 minus 6, we're going to give that formal charge of negative 2. Oxygen has 6 valence electrons, but it's only being assigned 4. So we're going to give it a formal charge of plus 2. And then the hydrogens again are both 0. So again, this assigns the less electronegative atom the more negative formal charge, so we can roll this one out. If we were to go back to our drawing of aluminum bromide, so here's our drawing of aluminum bromide. Aluminum has 3 valence electrons, and it has 3 assigned to it. 1, 2, 3. Each bromine has 7 valence electrons and has 1, 2, 3, 4, 5, 6, 7 electrons assigned to it. So this structure gives us formal charges of 0. If I were to cross one of these out and make a double bond, that would make aluminum have instead of a 3 here, it would be a 4. This would have a minus 1. And bromine would be 7 minus 6, so it would be a plus 1. And that would make the more electronegative element positive, and the less electronegative element have a negative formal charge. So we know that this is not the correct structure. I hope this helps. As always, if you have questions, let me know.